I'm at the Sandoval, and for the Choose Your Own Lab, or Lab 5, I chose the Falling Slinky Lab. The 5 parts of this lab are the introduction, the experiment, the code, the discussions, and conclusions. There are 2 sort of general purposes for this lab. The first one is to determine, using the correct fundamental physical principles, the effects gravity and drag have on falling objects. The second is to determine, using similar principles, the effects of static equilibrium on a falling slinky. The primary fundamental physical principle used in this lab is Newton's second law, which allows us to derive the position and velocity update formulas from the equation of net force, change in momentum over change in time. Other required formulas and principles for this lab include average velocity, position update, velocity update, static equilibrium, including tension, force, and gravity, weight force, drag force, the gravity constant, and net force with and without drag. The details of the experiment are as follows. Obtain the video of a falling slinky and analyze the slinky's motion and tracker. The next step is to edit GlowScript code using data from tracker and various fundamental physical principles in order to illustrate what the predicted motion of the slinky should be. The next thing to do is compare the findings of observed and predicted values, and then answer any supplemental questions and make conclusions. 2 main assumptions had to be made for this experiment. There was no movement of the slinky in the x direction, and I had to assume the mass of the slinky due to a lack of data. Below is a video of my tracking points in tracker, and I'm going to explain the details of / initial conditions. So the system is the slinky, the surroundings is drag, earth, etc., including everything else. And I assumed the object mass to be around 0.173 kilograms. I did this by looking up the average weight of an object, or of a slinky on Amazon, and converting it into kilograms. The initial position of the slinky, initial velocity, and time of final observation are all listed on the slide below. And I calibrated the height and sort of the distance of the video using the height of the man on the left. As always, there are initial conditions in the iterations of the computational model. As for the initial conditions, it was pretty standard as to the other labs. I inputted the mass of the slinky. I inputted the initial position and velocity of the slinky as derived from tracker, although it's important to note the initial velocity is 0 because the slinky was released from rest. I inputted the gravity constant near Earth's surface and the drag constant. Like other labs before, the drag constant had to be calculated through trial and error from just testing values until the final position of the slinky matched that on tracker. So there could be some discrepancies between that and the code, but that will be discussed later. The iteration of the computational model actually contained 2 parts. So 2 while loops are present in this computational model in order to accurately depict the motion of the slinky both before and after its ends meet. This is because the net forces acting on the slinky are composed of different sources between the 2 halves of the fall, so to speak. The first while loop, as depicted on the left, will persist until the 2 ends of the slinky touch in the air. So basically this will go until the bottom of the slinky starts to move. As per the usual, I had to calculate the F-net, which was used by adding the weight force and the force of tension. In this particular part of the lab, tension and gravity cancel each other out, causing the bottom of the slinky to remain motionless. I applied Newton's second law in order to predict the motion of the slinky by putting in the velocity and position update formulas as shown. Because the slinky was in static equilibrium during this portion of fall, the only force acting on it was its own weight, which is why the tension and the gravity have to cancel each other out. The second half of the fall and the second while loop are shown to the right. This while loop persists until the slinky touches the ground. The F-net was calculated a bit differently here, as I had to include the weight force and the drag force in the F-net equation. The slinky was no longer in static equilibrium, so the force of tension and the force of gravity didn't cancel each other out. And I again applied Newton's second law in order to predict how the slinky would fall. Here's a video showing the results of my computational model. So here are some graphical results from each stage of the lab. The slinky initially remains motionless on the graph, as its bottom does not fall until the 2 ends meet. This is depicted with the flat sections on the graphs. The observed and predicted motion graphs align similarly during the flat section of the graphs, as they both begin at rest at the same location. However, their positions going forward are off by some margin. Despite that discrepancy, their patterns of motion remain similar, indicating that the observed and predicted motions of the slinky match up. There are a few sources of error for this lab which can sort of explain why the 2 graphs don't exactly line up throughout the fall portion. So there is obviously human error. That could be through coding, trial and error with the drag constant, delta t values, etc. There could have been misalignment and miscalibration in tracker and the tracking points. I assumed the mass of the slinky, so if the mass wasn't exactly accurate, that could have affected the actual motion of the slinky. And the same thing with the Google search for the man's height, it could have been inaccurate. Also, assuming there was no motion in the x direction. So again, all these errors contributed to the discrepancies shown between the observed and predicted motion graphs. So there's a pretty important question that needs to be addressed. Does the bottom of my model stay stationary like in the video? The answer to this is yes. While my model does not depict a slinky as much as like a ball, the ball was set to mirror the bottom of the slinky like in the video. Because of this, the ball in my computational model does not begin changing position until the time step when the bottom of the slinky would have begun changing position in the video. After while this occurs, the slinky is in a state of static equilibrium where tension and gravity cancel each other out due to its net force equaling 0. It is not until the top of the slinky collides with the bottom, which is an external force causing the net force to not equal 0, that the bottom of the slinky begins to move.